Hello, everybody. Welcome back to our series of lectures about blood flow, blood pressure, and blood vessels. In this video, we will be talking about arteriolar resistance. So let's get started. Okay, so I'm going to start with this figure here, which shows the distribution of blood to the different tissues of the body. Before I get into the details, I want to just remind you of a couple things. First of all, I want to remind you that cardiac output for an average person is about 5 liters per minute. That's at rest, okay? And then the other thing I want to remind you is that the systemic circuit um, consists of a variety of parallel circuits, right? So we have one circuit going to the brain, one going to the heart, one going to the liver and digestive tract, etc. Okay. What I want you to notice in this figure is that the blood is distributed unevenly to our tissues, right? So we have about 14% of our cardiac output going to the brain, about 21% going to skeletal muscle, 20% going to the kidneys, etc. So you can see it's not even to each of these tissues, okay? The other thing I want to point out is that these are the values at rest. So if we are not being active, but this distribution can be changed based on our need. So if we just ate a huge meal, for example, we can direct more blood towards our liver and our digestive tract to process that food that we just took in. Or if we're doing a lot of running, we can direct a lot of blood here to our skeletal muscle, okay? And this is something that you know from experience, I think. You probably have been warned at some point in your life not to go swimming or do some other exercise right after you've eaten, right? So the reason for that is because a lot of your blood supply at that point in time, right after you've eaten, is being directed towards your digestive tract and away from your skeletal muscles. So what's going to happen is because your skeletal muscles won't be getting their usual blood supply, they can run out of ATP and you can cramp up, okay? And if you're swimming, you could die, or at least that's what your mom or your grandma or whoever, would like you to think. And it is possible. Okay, so I want to make sure that I emphasize this point here, that the total blood flow to the tissues is going to be equal to the cardiac output. So if you were to add up the blood going to all of the tissues in the body, they would add up to the cardiac output. That may seem obvious, I don't know. And that the total blood flow to the lungs is also the same as the cardiac output. Basically, because this circuit is a closed circuit, you have to have the same rate of blood flow at every point in the circuit, right? So the blood flow through all of the capillaries, if you were to add them all together, would be cardiac output. The blood flow through all of the venules, if you added them all together, would be equal to cardiac output. The blood flow through the lungs is going to be equal to cardiac output. Because if you don't have that happening, then what's going to happen is you're going to end up with a backup of blood somewhere in your system, which is going to be bad. Okay. Okay, so I just talked about how we direct, or the fact that we direct different amounts of blood to different targets in our bodies. But now I want to address this question of how do we do that, basically? How do we alter the blood flow to the different targets, especially given the fact that we do it, that this is a dynamic process, that we change this from moment to moment based on our need, okay? The answer to that question is arteriolar resistance, okay? So we adjust the blood flow through our arterioles, and in so doing, we adjust the blood flow going to the targets that those arterioles lead to, okay? So that's what's kind of illustrated schematically in this cartoon. These little screws are meant to represent the fact that you can change the radius of your arterioles in order to change the resistance of them. So you could, for example, increase resistance going to this circuit and decrease the resistance going to these circuits to direct more blood to these circuits right here and less blood to this circuit right here, okay? Again, I want to emphasize this point that the total blood flow is going to be the same, right? So the total amount of blood going through all of the arterioles is not going to change. You're just changing the way that that total blood flow is divvied up, how it's directed, okay? So let's take a look at this in this example here. So as I already made reference to, I believe, we change arteriolar resistance by changing our radius, okay? So just remembering Poiseuille's law and remembering the fact that little changes in radius can have a huge effect on your resistance, okay? Let's take a look at this example here. So we have 4 liters per minute coming in to these 4 arterioles here, A, B, C, and D. Right now, they all have the same resistance. Therefore, each arteriole is getting 1 liter per minute going through it, okay? But what do you think is going to happen if we constrict arteriole B? Okay, so take a moment to think about that. Pause if you need to. Okay, so if we constrict arteriole B, in essence, we're increasing the resistance there, which then is going to decrease the flow, right? So we decrease the flow going through B, and as a result of that, we're going to end up actually redirecting blood through A, C, and D, okay? So again, I want to point out, you don't really need to pay attention to the actual calculations and the actual numbers here, but I do want to, again, make that point that you are still getting the same total flow, right? So you have 4 liters per minute coming in here. And then because we're assuming this is a closed circuit, we have these 4 arterioles here. These are the flow through these 4 arterioles are still going to have to add up to the same as this, okay? So they're still adding up to 4 liters per minute, which means that in addition to reducing the flow through B, we've actually increased the flow through A, C, and D, okay? All right, so I've already made this point that the total flow is unchanged in the second scenario. I do want to also bring up these terms that I think you already know that I've already mentioned at some point in this class. Vasodilation. So the term vasodilation means an increase in blood vessel diameter. Vasoconstriction means a decrease in blood vessel diameter. Okay.